Hey everyone, Chris at FiltMath here, and we're going to talk about trigonometry at C4 A2 level. Basically, just using the addition formula and subsequently the double angle formula. Our objectives for today are as follows: proof of tan addition formula, the use of addition formula to find an exact value, and solve problems in the form r sine theta plus alpha. If you want to click on the screen at any of these points, it'll take you straight to that example. Remember, this is just going to be a recap lesson rather than any kind of replacement for a full lesson and the full understanding that goes with that. But this should give you an idea of an awful lot of the types of questions that will come up in a C4 paper or in a trig section of a C4 paper. So, the introduction is this. So, trig, it's a topic that never seems to have any end of uses and applications. Right back to GCSE, right the way through, it seems like at every stage you have been introduced to a new use of it or a new slight variant on trigonometry, and C4 is no different. There was quite a heavy dose in C3, and C4 is pretty much the same. So I'm going to take you through a few types of questions. The first one is this: use the sine and cos addition identities to define the tan addition identity, or if you want, to prove it. So we're going to use the sine and cos addition identities to prove the tan addition identity. And what you need to know, well, you're given 4 of the identities in the formula booklet, and they are cos of A minus B. So cos of an A, angle A, minus cos of an angle, minus angle B, is cos of A cos B plus sine A sine B, and cos of A plus B is cos of A cos B minus sine A sine B. Just the signs are really reversed from what is in the original expression. And the sine A plus B is sine A cos B plus cos A sine B, and sine of A minus B is sine A cos B minus cos A sine B. And as you can see, those signs in the middle match what's in the original expansion. Okay, so this is a proof you may be asked to define. What do we know about sine, cos, and tan? What do you know that links them? Well, we know that tan is equal to sine over cos. Therefore, we can use that tan of A plus B should be sine of A plus B over cos of A plus B. And once I substitute in my values for sine A plus B and cos A plus B, I should get this. So if you look on the left here, you'll see sine of A plus B is that one there, and that corresponds exactly with that line there, sine A cos B plus cos A sine B. And if I look at the cos A plus B on the left there, that corresponds to the cos A cos B minus sine A sine B. Now, for those of you that are keen and know what you're doing, if I tell you that the next step is to divide each of the 4 terms by cos A cos B, you can do the rest, right? If you want to pause the video, give it a go, certainly do. Otherwise, I'm just going to continue on and show you what happens. So each of the 4 terms, so the sine A cos B, I'm going to divide by cos A cos B. The cos A sine B is going to divide by cos A cos B, etc., etc., and same for the other 2 terms. Once we get to this stage, we can cancel out a lot of terms. Well, if you look at the bottom left here, these 2 terms, cos A cos B, cos A cos B, are exactly the same. So they will cancel each other out directly, and they will just give me 1. Anything divided by itself will give me 1. The cos B and the cos B above that will cancel out, and the cos A and the cos A in the top line will cancel out. Nothing cancels out in the bottom line. And what we're left with is an awful lot of terms that cancel out to give us 1, but then an awful lot of terms that are sine of an angle divided by cos of the same angle. So like the sine A cos A, and they will become just tan of the angle, or tan of the angle A. Same as sine B over cos B is going to become tan of B. Once I simplify all that down, I will get my proof to be tan of A plus B equals tan of A plus tan of B divided by 1 minus tan A tan B. You can try and prove the other identity yourself. By the other identity, I mean tan of A minus B, but you should get tan of A minus B as tan A minus tan B over 1 plus tan A tan B. These are also supplied in the formula booklet, but you may need to prove how they are proven. You may need to show how they're proven. Probably would be much better English than what I've put there. No excuses, being a maths teacher. I shall not throw the same old tropes about I'm good at it, maths and not English, blah blah blah. Poor grammar. Okay. Trigonometry has many different types of questions. How about finding the value of a trigonometric ratio you don't know? One of my favourite words, trigonometric, rolls off the tongue. something like this. And this is from January 2008, I think is the past paper that's from. Using the tan A plus B expression, find the exact value of tan 22.5. If I tell you that the hint B equals A, if you want to go ahead and do it yourself, but it says to use the formula of tan of A plus B. Now, one of the most common uses for the addition formula that we have here is to use them to get what are known as double angle formulas. And this happens when B is equal to A, so that we get tan of A plus A. It's like adding the two bits together with them being the same. And in that case, we replace all the things that were tan B in the previous identity with tan A. So we'll get tan A plus tan A divided by 1 minus tan A tan A. Once I group those terms together, this becomes the much simpler tan of 2A equals 2 tan A divided by 1 minus tan squared A. Okay. It's common to think that the tan 2A would be equivalent to the tan 22.5, but we don't know the value of tan 22.5. So what we'll do is we'll let the tan 22.5 kind of be what the tan A was, which would mean that we're going to get tan of 2A, and tan of 2 times 22.5 is tan of 45, which we do know the value for, or certainly should. So we'll get tan of 45 equal to the expression on the right, and we know that tan 45, you can check in your calculator if you want, but that is equal to 1. So we'll get 1 equals 2 tan A divided by 1 minus tan squared A. I can then multiply across by the 1 minus tan squared A. And if I do that, I'll get 1 minus tan squared A equals 2 tan A. If I bring them all over to the right hand side so that I get a plus tan squared A, I will rearrange and get tan squared A minus 2 tan A minus 1 equals 0. Sadly, that doesn't factorize. It kind of feels, for instance, like it should. If it had been plus 1 at the end, it would have certainly fine. So we have to use a quadratic formula. And I've substituted the values for tan A, or for A, B, and C. A is equal to 1, B is equal to minus 2, as you can see, and C is equal to minus 1. I'll plug those all in. That simplifies down to plus 2 plus or minus root 8 over 2. Root 8 is 2 root 2, so that becomes 2 plus or minus 2 root 2 over 2. Divide each term by 2, and I'll get 1 plus or minus root 2. That is not the question quite finished yet, because we know that tan 22.5 is positive. So tan A must equal root 2 plus 1, and if you're not sure about how to work that out, here is a tan graph here, and tan 22.5 will be somewhere up in this region here, and that's between 0 and anything above 0. No minus numbers. If I do 1 minus root 2, that would give me something like 0.41, minus 0.41, something like that. So we know that the answer for that must be root 2 plus 1. I can also define the rest of the double angle formulas from the following identities as well. So the sine of A plus B and the cos of A plus B. These formulas are not supplied in the formula booklet. You should know how to spin them off the top of your head. If you've done any kind of practice for C4 as well, you'll certainly start to remember them off the top of your head. And just roll them off the tongue. So we looked at how tan 2A was set up, and it was used in the previous example. If I look at the sine, that would be sine of A plus A would then equal sine A cos A plus cos A sine A. These two things are exactly the same, so sine of 2A would just simply be 2 of those sine A cos A. That's quite simple, and maybe a rather bit dry and boring compared to cosine. When we do cos of A plus A, that's cos A minus sine A sine A. If I make both angles the same, instead of having an A and a B, they'll have both A. I can give a basic solution of cos 2A equals cos squared A minus sine squared A. That is not the end, because as we know, sine squared A plus cos squared A equals 1. And we can substitute in for the, say, the cos squared A, and to be 1 minus sine squared A, or for the sine squared A to be replaced by 1 minus cos squared. That gives us two new identities, one being cos 2A equals 2 cos squared A minus 1, and cos 2A equals 1 minus 2 sine squared A. These way around. You should kind of know these off the top of your head, especially for C4, because many integration problems, for instance, will ask you to integrate sine squared A, and you would need to use the rearranged version of this formula to do that. And when we come back to do our integration video, etc., I'll show you that. Okay, happy enough? We have time for a commercial break.
And now it's time for a breakdown.
Okay. Let's see. Another common type of question is where we can express a longer form of trig expression in the addition formula form. So it's kind of where we'll work backwards. You know, we kind of want it to be in the addition formula form, and we're given a longer expression. So something like this. Express 8 cos theta plus 6 sine theta in the form r, which is just a constant value, sine of theta plus alpha, where alpha is an angle we'll have to work out. Know your Greek letters, eh? Especially at C4. This one's theta, this one's alpha. Important. Historically, and going through the past papers, this is the most tested form of question at C4 in a state paper, so it's worth looking at. Okay, so the question's kind of in reverse when we get our answer, but we're actually going to start off by expanding the r sine theta plus alpha. So it's kind of our sine of a plus b. And if I do that, I will get r sine, each term is multiplied by r, will be sine theta cos alpha plus r cos theta sine alpha. Right. We know that that's equivalent to the 8 cos theta plus 6 sine theta. We should be able to put these two things side by side and they'll be the same somehow. Okay, so what we'll do, we'll put them equivalent to each other, like so. And then we will look at the bits that are similar in each expression. So we'll look for the term that has, you know, the sine theta here on the right, for instance. So which term on the left has the sine theta? Well, there's a sine theta there and there. The only other bit that's multiplied by that sine theta is a 6. So we know that r cos alpha must be equal to 6. Similarly for the cos, the two cos values are there and there. We know that the r sine alpha must equal 8. And that gives me these two expressions. So what do we know about cos? Cos, if I rearrange that, cos alpha will be 6 over r. And we know that 6 over r, or cos, is equal to the adjacent over the hypotenuse. Similarly, rearrange for sine alpha equals 8 over r equals the opposite over hypotenuse. And what we're going to do is we're going to draw two right angled triangles with the r being the hypotenuse, 6 the adjacent, and similarly 8 is the opposite, r is the hypotenuse. We can find out the length of r from these two triangles by using Pythagoras. So 6 squared plus 8 squared equals r squared, as you'll quite rightly know. If you do that, you'll work out that r is equal to 10, or even known from the expansion of the 3, 4, 5 triangle. So 6, 8, 10 are multiples of 3, 4, 5, which make a right angle triangle for Pythagoras, if you remember that. And we can even use tan to the minus 1 of the 8 over 6 to work out that alpha, this angle in here, is equal to 53.1. We found out a value for r, we found out a value for alpha. We write the answer in the form r sine theta plus alpha, which gives me 10 sine of theta plus 53.1. And that's that bit done. I hope that was helpful. I'll recap our objectives. So the proof of the tan addition formula, we went through that the first example. We used addition formula to find an exact value, we went through that in the second example, and we also proved the other addition formulas, or double angle formulas, sorry. And then we solved problems in the form r sine theta plus alpha. If you want to practice these, there is a link to the past paper questions. There's also a link in the top of your screen to go straight to that on the FlipMath website. There's other notes on the FlipMath website and other resources. Feedback on all resources should be sent to @FlipMath on Twitter. If you want to subscribe or like or give me any feedback, you can do so also underneath this video. Thank you for watching, and I'll catch you next time.